All right, so now that we've got part 6 behind us, our player and enemy interactions looking quite nice, let's go ahead and mark it off of our implementation plan overview. In this section, part 7, we're going to be focusing on implementing fully functioning cells. What does that mean? Well, that means we need to have the ability to spawn cells all over the screen by the end of this section. We need to make sure when we are spawning these cells that none of the cells overlap. Well, at least we need to do the best job possible at making sure they don't overlap. I mean, if they just happen to be an amazing player and get up to a point where we have tons and tons of cells, well, it's probably going to start happening. We need to make sure to implement cell death, meaning we need to go ahead and say, cell, you've been attacked, start dying. And then the cell needs to go, and it dies off, and it interpolates from green to purple, and at that point it's dead. But if it manages to die, it needs to give birth to an enemy. And it needs to be able to be saved by a player while it's dying, meaning that if a cell is in the middle of dying, if a player runs over it, well, we need to make sure that we account for that. And that is where we're going to check for player contact and save the cell on that player contact. And so the cell will simply scale out of existence, and then we no longer need to worry about updating it. So that is the mission of Part 7. Now, there's a lot that goes into making this part fully functional. So I am going to approach this in 2 different ways. I am going to first kind of lay out the objectives and then walk through the system that's going to get everything in place, and then start walking through each of the methods and how they need to interact with one another in order to accomplish everything we're looking to do in this section. Then I'm going to turn around and I'm going to flow chart out the major functionality of this section so that you can kind of get a big picture of what's going on. So that's the goal. So let's go ahead and start out by undoing all of this so we don't roughen up our overview. And we'll come over here and add a new whiteboard. Let's jump on up to the top, add a new one in, and begin by writing Part 7. We shall call it Cells. All right, so the first thing I'd like to do is a quick refresher back to the skeleton end of precision. If you recall, cells have states. Just like our game. Our game was able to be in several different states. Well, it had to be in one of several different states at any given time, such as the title screen, level changed, playing state, died state, etc. Cells also have different states they can be in. So let's go ahead and do a very quick review because these states are going to become very important in this section. So cell states. There's 4 of them. Cells can be healthy. Cells can be attacked. Cells can be saved. And finally, cells can be dead. So these are the different states that a cell can be in. And a cell is always in one of these 4 states. And there's a couple other things that I would like to remind you of. If you recall, we had a cell count that we had set up inside of cell. And cell count allowed us to keep track of how many cells remained in the level that was savable. Okay? Once this reaches 0, there's no cells left that can be saved. It's time for a level change. So, cell count, we also had an actors list, all the way back up in actors. If you guys recall, it's a static list, and this is the list that's going to hold everybody. So our player, our enemies, etc. But the actor list is going to become extremely important to us in this part for the simple fact we're going to be pulling cells out of it when they are, well, saved and no longer being drawn on the screen. It's funny, too, because you want to say we're going to be pulling cells out of the actors list when they die. Aha, but we're not, because we want to leave them on the screen to be drawn purple and dead. So in this actor list, we're going to have a whole bunch of cells, and I'm just going to draw a few of them up here right now as a reminder, because we're going to be dealing with this list very shortly. And cell count, let me throw a 6 in here. This means we have 6 savable cells left right now in the level. Now, we've got a few questions to answer in order to put this implementation plan together. Very simple questions. First of all, how are cells attacked? We need to come up with some sort of system. So how are we going to attack them? How do cells die? And let's actually start that with a, yeah, that's a good looking C. So how do cells die? And finally, how are they saved? Now, you may be thinking, well, cells dying simple. They get attacked and they die because you didn't get to them in time. And they are saved simply by running over them with your player if they are dying. And if you were to say that, you are correct. But that's not what I'm referring to here. What I'm referring to is what sort of system are we going to put in place to handle a cell's death? Basically, how are we going to make its life decrement away until it finally runs out of life and the cell is dead? And also, what are we going to do to implement a system that will allow a player to save a dying cell? Okay, so now the first one, how are cells attacked? That's the one you probably couldn't answer. How are we going to attack these cells? Well, basically, inside of our game class, we're going to come up with a timing system that we are going to use to attack cells. Now, since cells are randomly distributed all around the scene, it's going to look like we are randomly attacking cells. But the funny thing is, we're not. We're simply attacking them in order. Cell number 1, cell number 2, so on and so forth. But again, random distribution will make it look like random cells being attacked. So, let's go ahead and take a look at this timing system. So I'm going to come over here. Timing system, as a reminder, we are inside of our game class. And let me try spelling that properly.
You got some of my spelling going on there.
Oh, yeah. Inside a game class. And, well, really, it's going to come down to just a couple of things. We're going to create a new field called time until attack, and we're going to create another field called cell attack interval. So let's go ahead and do this. So first one, let's do cell attack interval first. So I'm going to actually give them to you in reverse order. So cell attack interval. And the other one, time until attack. Okay, time until attack is going to contain a number that is going to be decremented away, and when that number gets to 0, so when time until attack is at 0 or less than 0, that means it is time to attack a cell now. Okay? Cell attack interval, it's going to be kind of like a constant. A constant would go in there and we'll say the screen width is 800, period. Well, cell attack interval is going to be set to a value of 1. But we're not going to set it up as a constant, and here's why. That value, 1, represents seconds. In this case, 1 second. That is our attack interval. We're not setting it up as a constant for the simple fact that you may want to come back in here and change up your game logic a little bit such that as levels progress, your attack interval gets shorter and shorter. So your cells get attacked quicker and quicker as your levels get higher and higher. If we were to create this as a constant, well, you can't change it. So we're going to leave this as a non-constant, just a regular field that you can manipulate with game logic code if need be. Time until attack is basically going to be initialized each time we get ready to start a counting down to the attack of the cell, we're simply going to initialize time until attack to the cell attack interval. All right, beautiful. Now, the rest of the time we're going to focus code inside of the game class's update method. Okay, so once again, we are still inside game class. So here we are, update method. Now inside the update method, keep in mind, we're having to account for what game state we are in. There are several different states. Now, time until attack represents the number of seconds until we're going to attack a cell. When do we want to have time until attack decremented? Well, not right away, for the simple fact that what if we were sitting at a title screen? Okay, so is our game state playing? No, we're not playing the game. So do we need the time until attack to be decremented? No, I think not, because if we allowed it to be decremented all the way down to 0, the moment you started playing the game, you'd instantly have a cell attacked. And we don't want that to happen. We want you to begin the game and 1 second to go by before the first cell is attacked. This means we need to focus all of our logic for handling cell attacks inside of the game state playing. So inside update. Actually, I'm just going to do it over here, give myself a little bit more room. So inside update.
Since all of this is to happen in playing, since what it all boils down to is that the timing system is part of gameplay, just as much as anything moving around the screen. It interacts with the gameplay, so we only want to calculate it in the playing state.
But it only makes sense. You don't want to be sitting there at, died or the title screen, for heaven's sakes, and have stuff going on with the cells, like them being attacked and time until attack being decremented. You don't want any of that going on. You want all of that on pause until we get into the playing game state. So I'm going to say in update, in the game state equals playing section of code, so that's what that means. Again, I'm pseudo-coding here. We need to start chipping away at time until attack. So let's go ahead and jot that down. So time until attack.
Because really what that means is not only is time going by because we're in update, time is going by while playing. So you could say playing time is going by.
That's right.
And that playing time is what we're looking for. So in this case, we decrement attack time since we're wearing away at our playing time.
And everybody has seen this now several times. I'm going to abbreviate it for the rest of this video after I write it out this one time. Whew. Now recall, game times dot elapsed game time is the time between updates. So this is the time since our last update. And we've already talked about there being 60 updates in a second. And that means that basically one slice of this boils down to being 0.01666667. Okay? So what we're going to do is we're going to take time until attack, which is going to start out being initialized to a value of 1 before we start playing. We're going to take that value and we're going to chip away at it 0.01666667. Okay? Actually, there's even more sixes in there than that. But we're going to keep chipping away with it. If you were to take this number and multiply it by 60, after a full second, since we've hit update 60 times, what are we going to have? We're going to have 1 second. Very important in this case. So we'll simply take away our elapsed game time from time until attack every single time that we hit update and the game state is set to playing. Then what we need to do is simply check when we're dealing with the actor's loop to see if we're dealing with a cell. Now, what am I talking about? Well, if you recall, inside of the game class's update method, when we are in the playing section, we loop through all of our actors because we need to handle the player in one way, we need to handle enemies in another way. Well, now we need to handle cells. So, let me go ahead and do this. In actor loop, let's say that we just pulled out a cell. So, dealing with a cell. All right, so we have a cell in our hands. Well, what are we going to do? Well, we need to check to see if our time until attack is less than or equal to 0 and the cell is healthy that we are currently looking at. So all of this from here on down, let me try jotting that down again and make it look a little bit less bad. There we go. Is inside the actor loop. So what we're going to do is say if, again, pseudocode here, time until attack is less than or equal to 0, which means there's no time left. Attack now! But we have an AND. And the cell, if we were to query that cell state, the cell is healthy. That's very important. Because you don't want to attack a cell that has already been attacked. Because that's going to cause an interesting problem. So we don't want to do that because the cell's already been attacked. We've already said, here is how long it's going to take for this cell to die. Take care of yourself. If we were to turn around, come back in here again, and say, oh, attack, here's how long it's going to take to kill yourself, that's a little confusing. We've already told the cell to kill itself, and we've already said, here's how long it needs to take for you to kill yourself. So in this particular case, we need to make sure that the cell is healthy, okay? So inside here, what are we going to do? Well, the cell, if you guys recall, has a method called setAttack that we skeletoned in. And this is an instanced method. Let's call on this cell's setAttack. Attacked. So it's set attacked. And setAttacked is going to take in a time, basically. And that time is going to say how long is it going to take for the cell to die. So what we're going to do is we are going to send in a cell death rate. And this is going to be a constant that we're going to need to create when we code in part 7, Logan. So we'll just send that over. So cell death time.
And once again, this is really more of what I would consider to be a game parameter. How long is it the cells take to die? We'll define that as a constant, and then all the parameters are in the same, easy to change place.
Exactly. And we'll set this at, I believe we set it at like 2 seconds. So that's how long it takes for a cell to die. So that's how long you have to get across the board to save that cell. Now, after doing this, this is very important. What we need to do next is turn around and take that time until attacked and simply reinitialize it or set it back to cell attack interval. Let me go ahead and jot that down real quick, and then I'll talk about it. So time until attack equals, again, setting it back to the cell attack interval.
Yeah, the exact same line that was used to initialize it originally.
That's right. Very important. Because if we do not do this section right here, let's think about what will happen. Well, time until attack is going to be a value of 0 or less than 0. The next time we run the update method, okay, 0.01666667 seconds later, what's going to happen? Well, we're going to drop right back down in here. We're going to decrement, so let me go and point this out. We're going to decrement time until attack even more. So now it's going to go rather negative or further negative, and then we're going to come back in here, we're going to pull out our very first cell again, and if the cell happens to be healthy, we're going to attack it. Basically, we're going to attack everybody, okay, because at this point in time, it's time to attack. So each time we go through every single cell, time until attack is going to be less than or equal to 0, so every single cell that's healthy instantly gets attacked, basically. So we need to take the time until attack and set it back to the cell attack interval, guaranteeing ourselves that we will have X number of seconds until the next cell is attacked. So let's go ahead and terminate that off. All right, so this is kind of between pseudo and real code. So this is the section that we're going to do for dealing with a cell that's getting attacked. Let's take a look at the questions back in the upper right-hand corner of the board. First thing we needed to do is know how cells were attacked. Well, we've accomplished that. Inside of the game class update method in the game state playing section, we're simply going to use time until attack as a timing mechanism to control when a cell is attacked. And when time until attack reaches 0 or below 0, and we're dealing with a healthy cell, we're going to simply attack it, okay? And then reset time until attack to the next cell attack interval. Okay, so that leaves, well, how do cells die and how are cells saved? Well, cells die. That gets taken care of inside of the cell itself. Okay? So there's nothing we can really put here other than just some attack code. We've said, cell, you're attacked. And now he's going to start handling his death. But how are cells saved? That will be inside the game class update method. In fact, it will be the very next thing after the if statement that I just put down. So let's go ahead and do another if statement. Because I can come in here and say if the cell that we're currently looking at, if his state is attacked and the player is colliding with him. So I'm just going to put player collide. So if the cell state is attacked, that means we know he's in the middle of dying. Because when he's dead, he's dead. He's no longer attacked. So if his state is attacked and our player is touching him, haven't we met the requirements that we set forth for saving a cell? The cell is dying and the player touches it. So if this condition happens, we need to save the cell. So what are we going to do in here? Well, we are going to call on another instanced method over inside of cell. And once again, we've skeletoned this in. It is the save method. So we'll have cell.save. And, you know, here, even though we're not doing game logic type stuff, this is a great place to come in and do something with score. So score plus equals something, and we'll worry about that something later on. But, I mean, we've just saved a cell. Come on. You get scored, points for saving cells. So this is a good place to get some points.
Right, or to at the very least jot down a note and say, hey, when we have some way of storing score, this is where it goes. So we don't have to go and hunt around for it later.
I mean, this is an implementation plan after all, so, why not write some notes down for ourselves? All right, ladies and gentlemen, let's go ahead and come back up here to our questions. How are cells saved? Well, the trigger for it is inside the game class update method, right here. Okay, basically if the cell's being attacked and the player is colliding with it. There you go. Okay, so now that we've got that in place, let's go ahead and shift our focus over to the cell class and start talking about things like the set attacked method or the saved method. And how is the cell going to handle death, as we've got there? How do cells die? So let's go ahead and pull up a new whiteboard. Told you there was going to be lots going on in this one. All right, so now we are in the cell class. And we will be in here until I designate otherwise. All right, so the first thing that we called on from the update method back in the game class was set attack. So let's take a look at set attack first. And set attack took in some sort of death time, which is going to be how long in seconds it's going to take for the cell to die. So what are we going to do in here? Well, I'm not going to code all this out. Let's do some extreme pseudo coding here, and we'll just turn it into English. So what we need to do is check to make sure that the cell is a healthy cell, because we don't want to attack a cell that has already been attacked or is dead or whatever. Okay, it's just a precautionary measure to make sure that we are indeed dealing with a healthy cell.
And also to make its functionality make more sense, because if you were outside of cell and had no idea of its inner workings, you wouldn't want set attack to cause undesired or unexpected things to happen. Now, if it's healthy, then that's everything needs to happen. We need to set up the whatever timing, whatever code needs to happen. But we don't want to get into a state where set attack causes undesired things. Like we want attack to mean that the thing starts losing health. And if we're not careful about checking the state, we run into possible cases where set attack gets called over and over again. Mm-hmm. And then we have cells that won't die or won't go away, or all of them die, or any other bad scenario. So we want to be careful about when we trigger this.
Right. Let me point something out real quick. And that is, right here, I've said set the death time. But when we skeletoned in this, basically we called it death rate. But Logan and I talked about it. This is the whole idea of implementation plans. as we were putting together the fine-tuned implementation plan for this section, we both said, death rate, that doesn't really sound like a time. It's like, it's just not quite there. Death time makes a lot more sense. It's a little more logical, as in this is how much time is remaining.
Right, it just fit the way that we were describing cell death, because you had even mentioned earlier in this implementation plan that the cells will take 2 seconds to die.
That's right.
That is an amount of time over which death occurs. So therefore, death time makes a lot more sense. That way we can set this as a time in seconds, and we get the expected results. Whereas if we had something like a rate, that's actually a term that makes you think of, well, a higher number would be faster. Whereas an amount of time, a higher amount of time means more time to die or slower death.
Exactly. So I just want to point this out, that we will be changing the death rate over to death time when we jump into Precision, or inside Visual Studio, working on Precision. Now, the next thing we need to do, and this is very important, and that is to set the cell's state to attacked. Because we have just attacked the cell. Okay? We want to make sure that anyone else that's dealing with this cell knows that he is currently attacked. Okay? If we were not cautious here and did not set the state to attack or anything else, well, what happens? We still have a healthy cell. And this is going to cause a big problem, because is the cell healthy? Yes, he is. Okay, death time equals, and we'll just basically keep changing that death time to the current time. And we don't want to do that. We want to make sure that this death time gets eaten away. It's the time until he dies. So, well, actually, we're not going to eat away. We're going to use it to come up with a percentage. But the idea is we need to make sure that we make this cell marked as attacked.
Right, and that goes back to the whole reason of having states, was so that we could have the cell respond in different ways depending on its state.
Exactly.
And one of those things is to take into account attacked here. Well, and that goes along with set attacked. Set attacked, we want to remember that we set it to attacked.
Now this is attacking. Now remember, back over in the update method inside the game class, we also took into account the ability to save a cell. So let's go ahead and talk about what code can be found inside a save. It's really not much. So here we are, save. And inside of the save, what we're going to do first is make sure that we're not already being saved. Because when you run over a cell, let's think about this. What states do we have? It could be healthy, it could be attacked, it could be saved, or it could be dead. Okay? There are no other states for us to be in. So if you save a cell, he is saved. Now, when you first save a cell in the requirements, what did we put forth for the cell's reaction to being saved? He scales down. Okay? That means he's still alive. Okay? And he still needs to be drawn, but he's getting smaller. And since we know updates being called 60 times a second, well, that means we know that we're going to still see him, and the player could still be on top of him as he's shrinking down over in the game class's update method. So we need to, inside here, check to see if he's not yet been saved, and if he's not yet been saved, start the process and set the state. Okay? Otherwise, just ignore it altogether. Because think about it. You've got your player, you got your cell, he's dying, you run over him, the time it takes to get from here to here, updates probably run 50 more times, okay, or 30 more times. And in that 30 times, we've already started saving the cell. So we don't want to reinitiate save until you're off of it. So that's what we need to account for here. So let me go ahead and just clean this up a little bit and jot that down. So inside save, the first thing we're going to do is make sure that we are not already saving the cell. So if we are not already being saved. So if we're not already being saved, then we can do the following. We can start a scale. So start a scale to 0, and we're going to do this over the cell save time. which I believe we skeleton this in.
Right, that should be inside of cell itself. It's similar to the idea of, what was it, enemy scale time. There was an enemy scale and value that was similar.
Yeah, so we've already got the skeleton in, so we're going to use it. So basically, we just said, hey, you've not already been saved, but he was attacked and the player ran over him, so hey, let's save you. And the way we're going to do that is by telling you to start scaling down to 0 over the cell save time, over that much time. Then we need to turn around and set the state to saved. Because remember, to get in here, he wasn't yet being saved. His state was not yet saved. It was still attacked. So that's it. That's all we need to put in to make save work. Now, update. The heart of the cell. This is the guy that's going to be responsible for making sure that he dies off. Okay? Or what happens if he gets saved. So let's go ahead and jump down. Throw in update. Now, update, we've got two things to look for, and that is if we're attacked or if we're saved. So let's just jump right into the nitty-gritty and start out with if attacked. If we're attacked, we need our life to be drained away from us. And if you recall, we set up a life percent field. So what we're going to do is take that life percent field, which is going to start off at a value of 1, indicating full health. And we're going to decrement that all the way down to 0. When it hits 0, we're dead. Okay? So let's address it. Life percent. Well, I said we need to decrement, so let's go ahead and say life percent equals life percent minus. Now, what are we going to subtract away from it? We need to take away a percentage, okay? And now we're dealing with a death time. So how much time do we have before the cell is died? You know, it's X amount of time. All we need to do is take our elapsed game time, total seconds, and divide that by a death rate. And that's going to give us basically our percentage, our life percent.
Right, because elapsed time, total seconds by itself, if used by itself, would always result in the life percent draining over a course of 1 second. That's why we have the death time field, so that we can adjust that. So it would be very easy to set or change that. So that's where we take the total seconds, or what would end up being 1 second after we do 60 updates, and then divide that. So that way if we divide that, we're dividing by, if we had a higher number for a higher number of death time seconds, then it would end up taking longer. Because if we set that divided by 2, then it would take twice as long. Because we're decrementing by half as much life percent each time.
Exactly. By the way, I promised I was going to do this. So there we go. That's game time dot elapsed game time. Okay, just too much stuff to write out. So here we are. We now have this percent, this life percent number decrementing away from 1 to 0. So we need to check, after we decrement it away, did this calculation that we just performed, did it kill us? So we'll turn right around and say, I'll just say if died.
Right, since this is the place where life percent gets decremented, this is going to be the first place where we'll know if the cell has died. Because the very moment that life percent hits 0 or drops below 0, then that's it. We're out of life and have died. So that check is going to be put in place immediately after we do this. So we don't worry about doing any further updating until we check to see if we have died.
There you go. I just added that in. Life percent is less than or equal to 0. First thing we're going to do, if that is indeed the case, is take our state and set it to dead.
Now, this may seem obvious because we have a dead state. We're checking for died, but it goes one step beyond that. If you notice, this entire section was only reached if we were in a state of attacked. And so by setting the state to dead here, what that means is we'll never get back to this place in code. Or rather, this code will execute exactly once.
Yep.
Because what you've just written down now is another thing that we need to take into account. The cell count being decremented, we don't want to have that happen multiple times per cell.
Right.
Otherwise, one cell could end up eating up all of our cell count.
And it's time for a level change.
Yeah, and one cell dying could cause odd things to happen.
Right. So in this particular case, we need to decrement cell account because we no longer have a savable cell here. This cell is dead. He cannot be saved anymore. So we take cell count, we decrement it once. That means we're one step closer to a level change. Okay? So the final thing we need to do if this just happens is create an enemy at the position that we being the cell, just died at. So create an enemy at our position. And that is going to be a call to a new method we're going to need to write called add enemy at, and we'll just simply send a position. And add enemy at will simply spawn an enemy at the position we send, and he'll begin scaling up, which will make it look like he's climbing out of the dead cell. Okay? So that's everything that we need to do if we just died. Now, of course, the cell state is attacked, so there's one more thing that we need to do, and that is simply adjust the tint. I'll say adjust color. Because remember, we're going to change over time as we're attacked from a healthy color, which is going to be a greenish color, to a dead color, which is going to be a purple color. So we need to interpolate between the two colors over time, and this is how we're going to do it. We're going to implement that lerp method that we set up. And lerp is going to take in dead color. It's going to take in a healthy color. And it's going to take in that life percent that we've caused to get smaller and smaller over the cell's lifespan as he's attacked. Okay? Now, what do we have here? Well, we basically have an interpolation setup that looks very similar to what we saw when we were implementing the enemy movement a couple videos back. Where, remember, we had basically a point A, a point B, and an amount to control the interpolation between the two amounts, and that amount went from 0 to 1. Well, life percent's a little different. Life percent goes from 1 to 0, so we're actually going backwards in our interpolation. We're going from healthy color to dead color. We're going this way because life percent starts at 1 and it gets smaller, 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 smaller until we finally hit 0. So the exact same setup here that we had over in the enemy section, except in the enemy section, if you recall, for movement from point A to point B, we used smooth step, and in this particular case, we're going the opposite direction, and we are using linear interpolation instead of smooth, so we're going to get this straight line like such.
Right, that's a return from, once again, from 1 down to 0, and that's why dead color and healthy color appear swapped.
That's right.
As opposed to when we had point A and point B, where we're going from A to B. Here, it's in essence going from B to A. So that's why we put dead color first, is we're actually going from healthy color to dead color, because we're going 1 to 0.
Right.
So that's an explanation for why the dead color and healthy color are swapped there.
Now we've got another if. Now we need to check to see if we're saved. So if state is, oh, here I go coding, isn't that funny? So if state equals saved, and, very important here, the cell is not scaling. Once again, a cell is attacked. It's dying. Its color's changing. We walk over it. We've now saved it. We call on the saved method back up here. What does the saved method do? It starts a scale. We don't want to immediately pull this cell out of the actors list, because the actors list is responsible for making sure everybody gets drawn, because we're going to loop through all of the actors in that list and call on each of their draw method. So we cannot pull this cell out of the actors list until it's done scaling all the way down to 0. Once he is scaled all the way to 0, then we can remove him from the list, and that's what we're checking for. If the state is if the cell's state is saved and the cell is not scaling, that means we have already scaled all the way down to 0. Now we need to do two very important things. We need to remove this cell from the actors list, and we need to decrement that cell count once again, because this cell is no longer considered a savable cell. He's already been saved. So let's go ahead and write that in real fast. So remove cell from actors list and cell count minus. And there we go. And this guy out here finishes off the update. So that is what needs to take place inside the cells update in order to properly handle attack cells and cells that are saved and no longer scaling. Okay, Logan, is there anything you want to add into this section here?
Let's see, nothing comes to mind. Just one thing to point out in that the attacked state, the code inside of that, obviously gets called a lot. The whole point of that is to cause an interpolation of sorts, both over life percent and then over color. The second if statement is just a one-time thing, because saved is going to become the state right after we call saves, or very quickly it'll be saved, and this check will go past saves many times. It'll be saved, well, for an amount of time, probably half a second.
Right.
But it's only going to trigger once, because when it's saved and then stops scaling, because you can almost read it as saying, if saved and we have stopped scaling. Because we know upon scale we're going to start scaling, so that's already taken care of.
That's right.
But when scaling stops and we're saved, then at that point the cell is already invisible off the screen, and then it can be removed from the list and cell count decremented.
Exactly. We go ahead and pull this back up. Let's see. Come back in here. Jump back up to the top real quick. So that took care of the how do cells actually die. We've seen that's handled inside of update. So now what I'd like to do is take a second and summarize all of this in a nice little block diagram for you guys, where I will do some more pseudocoding. Lots of good stuff here. So let's go ahead and create a new whiteboard real fast. And Logan, feel free to jump in with anything that you would like. We're going to start out back over inside of our game class.
So I guess what we're going to do is take an alternate look at the way everything is working in a diagram fashion. Because, I mean, everything's been written out. It's even been pseudo-coded.
Exactly.
But this should help look at exactly how one of the decisions flows into the other. Because we've seen a bunch of different methods and what they can do. But it would probably be helpful to see what causes those states, the checks by themselves, and then what they result in. So some diagrams might help with that.
So update, and all of this is taking place in the playing state.
Just to reiterate, all this is all gameplay code.
That's
so this is always going to happen in the playing state.
So we've got that time until attack getting decremented minus equals the game times dot elapsed game time dot total seconds. Now, I'm going to do ... and this is going to, and you know what, I can do the best I possibly can here, bear with me, to make this look like that really stunk. There we go. So there's that section right there. Now, other things are going to take place. Now we're inside of the actor loop, and inside here, if we have a cell, so if cell, I'm not even going to block that in. This is what I want to block in. If we have a cell, what are we going to do? We're going to check to see if, I'm going to abbreviate the heck out of a lot of stuff here so I don't have to write a whole lot. We're going to check to see if the time until attacked is less than or equal to 0 and cell is healthy. So, and healthy. If that is indeed the case, then what we want to do is call cells set attacked. And of course we'll send over some information, and we need to turn right around and take that time until attacked and set it back to the cell attack interval. Got to break it down like this, otherwise
there'd be no room to write the diagram.
No. All right, so now falling out of this, what's going to happen? Well, if state is attacked, so if attacked and player collides. So I'm just going to write if attacked and collides, so player collides. Then we need to call upon, with a better looking line than that, the cell's save method. And if we wanted to, we could do score stuff here later. Nice. So that is what needs to happen over inside of update in the game class. So now let's go ahead and shift our attention. Let me see if I can. Oh yeah, that's pretty close. Over to the cell class. First of all, set attacked. So in set attacked, we're simply going to come in here and make sure that we're healthy. And if we're healthy, then we need to set our death time so that the cell knows how long it's going to take for it to die. And we need to set our state to attacked. So all of this is for set attacked. So let me... How do you like that, Logan?
Oh, you've mastered the line drawing skill.
Well, thank you, sir. Oh, yeah. Pixel accuracy. So, set attacked.
And one thing just for clarity, on the decision boxes, maybe label, because of course yes is on a different side than it was in the game class. But just to make this
not a problem,
incredibly clear that we had the diagrams as yes off to the side, because that was just to show what was working there, so we could continue on to some other condition. But the set attacked is very simple, since if it's not healthy, then just do nothing. There's nothing to do otherwise. No further checks even.
Right.
There's just if yes, if healthy, then two things occur. So it's I guess you could say a more simplistic diagram in that case.
So saved is going to simply say, are we already saved? So if we're already saved, we need to simply exit. We need to return back from this guy because there's nothing that we can do here. If we start setting anything, it's going to cause problems. Why? Because we're going to turn right around and start a scale. Now we all know that scale to 0 means start a scale to 0. And then we need to turn around once again and set our state, and in this case, to saved. Alright, so let's see if I can clean this up just a little bit. Perfect. Okay, so that leaves only the update left to take a look at. Update's got a lot going on, so I'm going to try to jump up here as far as I can. And inside of update, we're going to start out by saying, or in fact, I'm going to move this over just a little bit to give myself even more room. Are we attacked? And sorry guys, I wanted just a little bit more room here. There we go. So attacked, yes. Well, what do we need to do? We need to calculate our life percent. I'm just going to put a percent Fair enough, Logan? So let's
sure.
calculate life percent. And then we need to check that percent to see if we are less than or equal to 0. So percent less than or equal to 0. If it is, so I'll just keep going down for my yeses. Then what we need to do is set our state to dead. And decrement our savable cells cell count. And add an enemy.
This is why you needed all that room, because if you remember back to the pseudocode, there was a fairly sizable block of code for the cells update. So just a few things that are happening here.
So add enemy at the current position of us. All right, and then shift our color. Make sure that color goes all the way over to purple. I'll just put shift color. As I'm thinking, what do I want to write here? Whew, okay. 2 seconds to let hand rest. Lots of writing. Okay, so after shifting our color, which is a call to our lerp, L-E-R-P, method that we're going to create, or implement in this case, let's turn around and check to see if we are saved. Don't worry, this will make more sense in a second when I draw all this out, when I connect all the lines here. So saved, and we are not scaling. I'll just put in not scale, but we're not scaling and we're saved. And if that is the case, then we need to remove this actor because we no longer want to draw this guy to the screen. So remove actor, or remove from actors list. Except we'll put a V in there. So remove from list and decrement that cell count. Because this is no longer a savable cell. And that's really it. From here, what always happens is we simply call on base.update. Okay? Oh, that's a great one. All right, so let's go ahead and jump back up here a little bit. So what happens if no, we're not being attacked? Well, we're going to come in right here. Actually, let me take that out just a tad bit further. Because if we're not being attacked, then we're going to check to see if we're saved and we're not scaling. Okay, so let's go ahead and put no up here. Now, life percent. Is our life percent less than or equal to 0? If the answer to this is no, that's fine. What we need to do is make sure we just shift the color because we're in the middle of what? Dying.
Right, we're attacked. And that's where it's a tricky case to draw up because we only change the color when we're attacked, but there's a possibility of doing more things when we're attacked. But if we are attacked and we're dead, then we'll do all of these things all together. So it's an interesting case of scenarios.
And then in this case here, we'll just simply come out and call on bases update. If we're not saved and not scaling. Whew! All right. So there you go. This is the grand picture of what is taking place with our cells. Okay? But there's more. It just never ends. Oh, like I said, this is really a pretty big section here. So now what we need to do is we need to have some sort of means of adding cells into the scene. Just like how we had an add enemies method that we could call on and say, look, you have this many this many enemies, create them. Well, we need to have the same thing in place for our cells. So we're now going to shift focus away from the heart of the cell system and start looking at almost like some little utilities in a sense. I mean, some of these still play very vital roles, but you get the idea. It's not the heart of controlling life, death, the universe, and everything. Okay, so what we're going to do is we're simply going to add an add cells method inside the cell class. And with it, we'll take in things like the number of cells that we won't create it, texture, healthy color.
And a lot of this should be familiar from the add enemies, because what add enemies did is the important thing about add enemies was how many. The rest of the things it took in were just to satisfy the constructor when making a new enemy.
Exactly.
So the same deal here for cells.
So all we're going to do, once again, is simply create a loop. I'm not going to write all that out. But we'll have a loop, and inside of our loop here, what we'll do is we'll go in there and we'll create a cell. So to abbreviate, cell equals a new cell, with all that stuff set. And then, this is where things become really important. We need to position him randomly somewhere, right? So we can come in here and say, look, let me clean that up just a little bit. We can say cell.position, since we now have an actual cell, equals, and we can call on that game1 dot the get random screen position method that we went over carefully when we were dealing with setting up enemies. So get random screen position. And all we got to do is send in the cell's radius. So we have no accidents where the cell is partially drawn off screen. Okay, so we'll send this in. But now here's the kicker. Right now, if we just leave it at this, we'll generate a random number of cells that are indeed randomly scattered throughout the scene. Problem is, we have nothing in place to check and see if the cell we're about to draw is possibly drawing over part of another cell. So what we'll need to do is account for that somehow. And the way we're going to account for that is we are going to jump over into actor. So in actor, we are going to create a check collision with any method.
Because right now, collisions with the static check collision method require you to have found 2 and only 2 actors, and check those 2 actors and see if they're colliding. What we need now is to see if a cell has been placed on top of another cell. We don't know what other cell that might be.
That's right.
So we need someone saying, well, go through everything, see if we're colliding with anything out of the actors list. And really the funny thing about this is it turns right around and uses the existing check collision method, but it goes through and sets up the parameters. So it sets up whatever we call this for. So we're looking at a specific cell and seeing if it's colliding with any. So it knows to take itself. And then inside of that loop, if you're doing the loop through actors, you're going to get each actor out one by one. So you could take each of those actors and plug them into the second part of the check collision, and there we go. We just run that over and over again for all of the actors, and we end up with a result based on whether we collided with anything.
And I'll use that little bit of time to write what Logan was just saying. So here we are with calling the actual check collision that you're already familiar with, because we now have an actor A and actor B. We have this, the one that we're currently dealing with, and the actor we just pulled out of the loop. And then if they do collide, then we can just simply turn around and return true.
Right, because that's with the check collision with any is just that. The moment we hit even so much as one collision, well, that's it. We have found a collision. We don't need to check the rest of it, so we'll return at that point.
Otherwise, we're going to return false.
Right, but if we make it to the end of the loop and haven't returned true, then we're out of actors and none are colliding, so we return false.
Ta-da!
And then one thing to point out that you were drawing in while I was talking is that there's a check of where actor is not equal to this. And that's because when you said loop through actors, that does mean every actor, including this, including the actor
including ourselves.
And we don't want to do a collision check with ourselves because that will probably result in 0 or not a number. So, I mean, we don't want to check ourselves for a collision because we know we don't collide with ourselves.
Exactly.
We want to collide with something else.
Exactly. So what we need to do now is take this check collision with any, go back up to our loop up and add cells and use it. And the way we'll do that is we're simply going to set up a counter. So somewhere in here we'll simply have a counter. Let me think, how do I want to do this? So we're going to have 2 loops. So we're going to loop here and then we're going to do a cell counter. So actually let me just call it counter. And we're going to start the counter off at 0. And then we're going to create a loop inside. And what we'll do is we're simply going to set this guy, and then we're going to increment the counter, and then we're going to turn around and check where we set him at. Did we collide with anything? And we're going to use that old cell placement retry constant that we created in the skeletoning in section to see if our counter is still less than that. So we'll continue doing this loop. Now, if you guys recall, cell placement retry. This guy held the number of times we will continue trying a new position for a cell. So we're simply going to put the cell down, we'll increment the counter, and then we'll turn around and we'll check to see if we have collided with anybody. And we'll also check the cell placement retry to make sure that our counter is still less than that, okay? So as long as if we've collided with anybody or our counter is less than, we need to keep doing this and keep doing this until we get all the way up to the point of where, we may have just exceeded, our counter just exceeded that cell placement retry. And then if it did, that's fine. Just leave the cell at the last place we dropped it. And yeah, he's partially overdrawing somebody. So be it. There's so many cells on the screen right now. That's just the way it's going to have to work out. This guy's obviously really good. Logan, you want to add anything to that?
Right. The idea is that is to have the cells dispersed and not colliding over each other. But the method used is actually rather simple. It's just to try again. Basically, either it worked, so it's not like we move it an amount to get it lined up, because then we'd have to worry about other cells that might be around it. So instead, we just say, it's like, was this a good place to put a cell? No, okay, maybe it wasn't. Okay, try any other random place. Is this a good place? Maybe it wasn't. The idea is that if there's not many cells on screen, it will probably take very few retries to get a good random position.
Right.
But the cell placement retry is put into place as a limiter to make sure that we don't go crazy if we have too many cells. Because the problem with this method is that if there were too many cells, like let's say you were to very conveniently place like cells over the entire screen, and then try to place one more cell if there was no open space, the loop would never finish running because there's nowhere it could place a cell that wouldn't collide, and your game would just lock. That's where cell retry count comes in as kind of a safety to the mechanism to say it's like a give-up threshold. It's like, look, we've tried 100 times and we haven't found a good cell position. Let's just give up. Sure, the cell might be overlapping some of the cell, but that's better than having the game lock.
That's right. So that takes care of add cells. And Logan, to be honest with you, there's only one more thing I want to talk about, and that is that lerp method that I mentioned a minute ago, who's going to be responsible for driving the color from one color to another. Okay, so let's go ahead and just jump down here. So we can look at this as just kind of another utility type of method. So how is this one going to look? It's going to look like this. He's going to return a color. He was called lerp for our linear interpolation. He takes in color 1, color 2, and an amount. That's a float. Now it looks even more like that call to smooth step as we're using the word amount here. Inside, it's really simple. All we're going to do is we are going to use a math helper linear interpolation method to interpolate between one color to another. But we need to kind of split the color apart to do this.
Right. See, what it comes down to is it's kind of a balance between how deep we go into the interpolation. On one hand, we're not going to go so far as to write the mathematical interpolation ourselves. That already exists in Math Helper. But the functionality that exists in Math Helper operates on floats. It operates on a single number at a time. The problem is we don't have one number, we have a color. But where we can kind of compromise and meet halfway on both of those ideas is that a color can be thought of as 4 numbers. A color really has a red component, a blue component, a green component, and an alpha component. With those 4 components, those 4 number components, one can describe a color. So that means you could take a color, any color you want, break it up into its components. Each of those components are numbers, which can be applied to lerp, and then we can put them back together.
Yeah, I just realized this, Logan. You got to take credit for this one. I've been copying your amount forever.
Oh, do we have a printout of that bad spelling by any chance?
That's awesome. Ladies and gentlemen, I just now realized this has made it into pretty much every single video. Heck, it may have even made it into some of our code.
Nice.
That's okay. We can't spell. Look, I kind of live by this motto. If it doesn't say syntax error, it's spelled right. So, all right, let's try to actually spell amount right for just one video. All right, so byte R, and then we'll repeat this for G, for B, and Logan said alpha as well.
Right. I wanted to include alpha because that is a possible setting for a color. A color can include an alpha channel. So I figured, why not? Since we've already taken the effort to break this down into components, let's break it all the way down. And the nice thing here is if you happen to use the alpha of any color, it will work properly with the lerp function.
And same things happen. I'm just saying repeat, because the line is literally repeated. Color1.r, or excuse me, now we're going to go for green to color2.green by amount. And then we'll continue to do it. So R, G, B, A. G, B, A, and then amount. But the way we can spell it, just for one video only. Now, when we've calculated all of these new variables containing an element of color, we need to simply assemble it back together as a color and return that back. And the way we'll do that is simply say, look, return a new color. And for creating this color, let's pass it R, G, B, and A. And that's it. And all we got to do is pass in color, amount. That's it. Amount's going to simply drive from one color to the other. So remember, since we're going from 1 to 0, we go from color 2 to color 1. Okay?
Right, just in our current usage. If you used it somewhere else, you could interpret.
If you go from 0 to 1, you'd go from color 1 to color 2. So it's however you want to drive the interpolation between the two values.
Right, it just so happens that a life percent starting at 1 going down to 0 is our driving factor in this case. That's why we're going from color 2 to color 1.
You got it. And with that, that's everything that we need to get in place in this section. Of course, we need to go ahead and add in the check collisions with any, but that's stuff that you guys have already seen, and we've talked about it briefly. And we also need to add in the add enemy at as well. And add enemy at is just going to be responsible for creating an enemy at a given position as opposed to a random position. So anything else you want to add to this implementation plan, Logan?
No, the only thing that was sticking out to me was the add enemy at, because you touched on that earlier. But like you said, it's very simple.
Yep.
I will point out that it's in the game class.
Yeah.
And this is just kind of a you can almost call it a compromise location until we get into more advanced topics. I'm sure if you've gone past the course where it's at now and you've studied those more advanced topics, you might know what we're talking about. But for now, we want to keep things simple, keep things based in things we've learned. So we're going to place that as a utility method, and we'll use that in order to get around a few problems. I might even point those out exactly why we're creating it once we're in the class and everything is made clear.
Okay. And so with that is going to wrap up this implementation plan. Thanks a lot.